Hello everyone, hope you are all doing fine. Welcome to another lecture on electrostatics. In the previous lectures on electrostatics, we have learned about Coulomb's law, which explains that the charges exert force on each other. Now the question is, how and why the charges exert force on each other even though they are not touching with each other? The answer is simple. Every charge creates an invisible field around itself. Okay, when another charge enters into this field, it experiences the force. That means the invisible field around a charge is causing the force on the other charge. So in this video, we are going to learn about electric field, its properties, and we'll also look into some of the examples based on the electric field. So yes, my name is Vijay, Krishna, and you're watching UpPhys channel. Let's get started. First, let us understand what is electric field. Okay? According to Coulomb's law, when the two charges Q and Q naught separated by a distance r, then these two charges exert force on each other according to the equation F is equal to K Q naught upon r square. Okay? Instead of writing this equation, I am going to write this equation in other way. Okay, right. I have taken the charge Q. And this Q is a charge which is creating field around itself. Now I have taken another charge of Q naught, and I have taken that charge from infinity or some point or from some other point to the vicinity of the first charge. That means in the field of the first charge. Let's say I have placed this charge somewhere here. Again, now the separation between them is again r. I am considering it as r. Now the field of this charge is exerting a certain amount of force on Q naught. Actually, as we are studying the force on Q naught, we treat this charge as a test charge. In some books, test charge is defined as it is a charge which creates no influence, no field around itself. Okay, so it is a small amount of charge where it creates negligible field, and it causes no influence on the other charged particles. Okay, so this is the test charge. Right, now let's say Q naught is the test charge on which force is F. F is the force acting on the test charge Q naught. What is the force on unit positive test charge? It will be like F by Q naught. F is the force on Q naught charge. Q naught is the test charge. Okay. F is the force on Q naught charge. Per unit charge, what is the amount of force? F by Q naught. It is something like 20 rupees is the cost of 5 pence. What is the cost of 1 pen? So F by Q naught, 20 by 4. Okay. Sorry, 20 by 5. So F by Q naught. This is what we call it as electric field. Electric field in some books, electric field is defined as force acting on unit test charge. Or this the definition can also be given like the force acting per unit test charge. Okay, so I am writing this equation again as E is equal to force on test charge by test charge. So force acting on test charge is F, test charge is Q naught. Simply I can write it as charge of test charge. Okay, so charge of test charge is Q naught. Force on test charge by charge of test charge. This is what we call it as electric field. Electric field. Since electric field is a vector quantity, I am going to write the vector representation as well. Electric field is a vector quantity is equal to force is again a vector quantity by charge. Charge is a scalar quantity. Charge is a scalar quantity. As you already know, electric field is a vector. We are going to write the vector representation of the electric field in terms of charge also and distance. So F is again a vector. Q naught, test charge, is a scalar. Is a scalar. Now electric field is given by the formula force by charge of test charge. So by using this relation, I can also write the equation for the force as F is equal to Q naught into E vector. Q naught into E vector. So very important relation. Okay. Now when you look at, F is equal to Q naught into E vector. So this is one formula for the electric field for the force between the charges. Okay. On the charge, especially we can say on the charge. Electric field due to the charge and force on the charge. Now let's move on to the next slide. And I want to write the units also. What is the unit of electric field? Unit of electric field is unit of electric field. Unit of electric field is force unit is Newton. Force unit is Newton. Electric field unit is electric field formula is force by charge. Force by charge. So force unit is Newton. Charge unit is coulombs. So Newton per coulomb is the unit of electric field. Unit of electric field. Now if I want to write the dimensional formula of electric field. Dimensional formula of electric field. Dimensional formula of electric field. As we already know, the dimensional formula of force, that is M LT minus 2, because force is MA. General expression for the force is MA. M dimensional representation M, and acceleration dimensional representation is meter per second square, which is LT minus 2 by coulomb. Coulomb is not a fundamental quantity, rather it is derived from the fundamental quantities such as time and current. Okay, current is a fundamental quantity. So if I want to write the dimensional formula for the charge, I is equal to Q by T, general expression I am writing. Q is equal to IT, where I and T are fundamental quantities. The dimensional representation of I is A and dimensional representation of T is T. So charge dimensional formula is AT. Charge dimensional formula is A and T. So what am I getting finally? M, L is there, okay, and 1 T, if it goes to the numerator, A minus 1, and T goes to the numerator, T minus 3. So this will be our answer, the dimensional formula of electric field. Dimensional formula of electric field. So the main key points that we have discussed in this slide is Q naught is a test charge. Why we are calling it as test charge? Because we are testing the force on this charge. We are bringing this charge from some point to into the field of the other charged particle. Okay. Now this field of the charged particle is exerting force on Q naught. That force is F. Force on Q naught is F. Per unit charge, what is the force? F by Q naught, which is E. Generally the electric field is defined as force on the test charge by charge of test charge. So force per unit charge. Force per unit charge, given formula is F by Q naught. I have rearranged this equation for F is equal to Q naught into E. I have to remember these formulas and the unit as well, and finally the dimensional formula. These are the points that we have discussed so far. Okay, and the key point is every charge creates certain amount of invisible field around itself. This invisible field around a charged particle is called electric field. If I want to elaborate it further, like mass creates gravitational field around itself, magnet creates magnetic field around itself, like in the same manner charge creates electric field around itself. Okay, so gravitational field is again invisible, magnetic field is again invisible. Like gravitational and magnetic fields, the electric field is also invisible. So gravitational field exists like around the mass. Like if we take the earth, there is gravitational field around the earth. Okay, if I leave an object freely, it moves towards the earth. It moves towards the earth. I am not giving any force, rather the earth is pulling the objects. That is what we call it as gravitational force. That gravitational force exists because of the gravitational field around the earth. Similarly, electric force exists because of the electric field around the charge. Okay, so hope the point that I have discussed in this slide is clear to you, right? Let's move on to the next slide. Electric field due to a point charge. Electric field due to a point charge. Okay, so let's say I've taken charge Q and another charge Q naught. Instead of taking the another charge Q naught right away, I've taken the charge Q. I've taken the charge Q. Okay, now this charge is creating the field around itself. Field around itself. Now I've taken another charge of charge Q naught. I put it right here, Q naught. Q naught. Now the force on this Q naught is F is equal to electric field due to first charge into Q naught. Into Q naught. I am not using this vector representation here. Okay, F is equal to E into Q naught. F is equal to E into Q naught. E into Q naught. Okay, now this equation can be rearranged as we already know. E is equal to F by Q naught. F by Q naught. Now let us suppose I kept this Q naught charge at a distance R from the first charge. From the first charge. Okay, now the force between these two is F is equal to, force between these two is F is equal to K Q Q naught upon R square from Coulomb's law. From Coulomb's law. Now I can replace this K Q Q naught by R square in place of F. In place of F. Now let's see what am I getting. So electric field due to a point charge is equal to F is nothing but K Q Q naught by R square divided by test charge Q naught. Test charge Q naught. If I cancel this Q naught and Q naught, what am I getting? E is equal to K Q by R square. K Q by R square. So this is the equation for the electric field due to point charge. Electric field due to point charge. So as I have already mentioned, every charge creates field around itself. Creates field around itself. That field is called electric field, and the electric field due to a point charge is given by this formula. Given by this formula. If we have capital Q here, then we will have to use capital Q here. Okay. So E is equal to KQ by R square. Now if you want to look at vector represent, as we already know, electric field is a vector quantity. If you want to look at vector representation of electric field, then what am I supposed to do is vector representation, vector representation E is equal to K Q by R square. I have to introduce a unit vector. Okay, unit vector along the line joining the charges. Okay. Now, this unit vector can be written as vector to its magnitude. Vector to its magnitude. So, electric field E is equal to K Q by R square. This unit vector can be written as vector to its magnitude. Vector to its magnitude. Now, this R square and R will become R cube. K Q by R cube into R vector. Electric field. The same procedures, same steps that we have followed in case of vector representation of Coulomb's law as well. Okay, in case of vector representation of Coulomb's law, we have obtained the expression for the force between the charges in vector form as K Q1 Q2 by R12 square into R12 unit vector, and this unit vector was further replaced with R12 vector to its R12 magnitude, and this R12 square, R12 cube, and this R12 has remained as it is. Okay, so K Q1 Q2 by R12 cube R12. Hope you have understood the steps that I have followed. Am I arranging this one? Am I erasing this one? Okay, so this is the vector representation of electric field due to a point charge. We can even obtain the equation for the electric field in terms of calculus based electric field expression. So electric field E, which is a small field due to the small element. Let's say the charge is very small. I've divided as a big object into a small piece, into small pieces. I've considered one piece and I'm measuring the electric field due to that small piece. dE is equal to K. The charge of small piece is dQ by R square, the distance of the point where I am measuring the electric field due to the small charge, into, this is the calculus based electric field expression. If I want to find the total electric field due to the entire object, then I have to integrate K dQ by R square integral. I can even say this equation as integral form of electric field. In this slide, we have seen the electric field due to a point charge, one thing, and we have seen the vector representation of the electric field due to a point charge, and the third thing is calculus based, integral form of electric field due to a small elemental charge. So these are the 3 points that we have considered, that we have learned in this slide. Okay, and if you want to compare the field equation with the electric field equation with the gravitational field equation, you will be able to gravitational field is something like G capital M by R square. You may be familiar with this equation with small g. Acceleration due to gravity, G M by R square. This is what we call it as gravitational field. Hope you remember this formula, right? The similar type of expression that we have obtained here, as you look at it. Here we have mass, here we have charge. The distances are again same, the point of interest that we have from mass to the point of interest, from charge to the point of interest. Okay, now K Q by R square, here K is Coulomb's constant, here G is universal gravitational constant. Okay, hope I made the point clear here. Now, so these are the 3 relations that we need to remember. Electric field in vector form, electric field in calculus form, integral form of electric field. Okay, now let's move on to the next slide. Let's look at the properties of electric field. Okay, properties of electric field. Look at the first property of electric field, direction of electric field. Electric field is a vector quantity that I have already mentioned multiple times, right? So it will have both magnitude and the direction. To find the magnitude of the electric field, we have the formulas. E is equal to F by Q naught is one type of formula. E is equal to K into Q by R square is another formula. Okay. So second formula, E is equal to KQ by R square is used to find the electric field due to a point charge at the point of interest. Okay. Whereas when field is given to you and charge is given to you, you can find the force. When force is given to you, charge is given to you, you can find the electric field. We use E is equal to F by Q naught. Now coming to the direction of electric field. As the electric field is a vector quantity, it will have both magnitude and direction. Okay. Now coming to the direction of electric field, if the charge is positive, if we are measuring the electric field due to a positive charge, let's say positive Q. If the charge is positive, then the electric field is radially outward. Radially outward. If the charge is negative, then the field is radially inward. Inward. Okay. Now I want to give you one more information here. Maximum intensity of the electric field exists near the charge. As the distance increases from the charge, the field strength keep on decreases. Electric field strength keep on decreases. So the maximum amount of electric field is possible near the charge, not exactly at the charge, near the charge. Okay, right. So direction of electric field is, when it comes to positive charge, the field is pointed away, radially away. When it is when we are using negative charge, the field is inward. Not the circles. I've shown these circles to show the strength of the field. To show the strength of the field. Do not use the misconception like these circles are the fields. No. Okay. Right. So we use lines to represent the field. Okay. Now the next point is, electric field is a vector quantity which we already know. Electric field is a vector quantity. We have K cube by R cube into R vector, or we can even use electric field is equal to force vector by Q naught charge. These are the formulas that we have already discussed. Electric field is a vector. How do we represent the vector direction here? Okay. As I have already told you, positive charge, if the charge is positive, then the field is radially away. Which arrow we need to consider to represent the direction? That's where we get stuck, right? So to identify which arrow is required, I'm going to consider a simple example, illustration. I have the charge here, let's say positive charge. Okay. Now I want to measure the electric field at this point. You are asked to find the electric field at this point. In such a case, what you are supposed to do is, you are supposed to draw a line that is connecting the point charge and the point of interest, the point where we need to find the electric field. Okay. Now if the charge is positive, then the field is radially away. That means the field direction is this one. Hope you have understood this point. Let's take another example. Let's take negative charge here. If the charge is negative and I want to find the electric field at a particular location somewhere here. Somewhere here. Okay. Somewhere here. In such a case, what you need to do? For negative charge, the field is radially inward. In such case, you need to connect the line joining the charge and the point of interest, and the direction of field is towards the charge. When the charge is positive at the point of interest the field is away. Field is away. When the charge is negative, then the field at the point of interest is towards the charge, this direction. Okay, towards the charge. Now here the field is in this direction, away from the charge. Away from the charge. These are the directions that we need to show exactly at our point of interest. Exactly at our point of interest to understand it even better. Now let's move on to the third one. Electric field obeys superposition principle. As electric field is a vector quantity, I've been saying it for 10 to 15 times. So electric field obeys superposition principle. Like electric force between the two charges obeys superposition principle. That is, the vector sum of individual forces is the net force. Electric field, net electric field is the vector sum of fields due to individual charges. Okay, so we can even give the statement for this superposition principle. Net electric field, or you can even represent this net electric field as resultant electric field. Okay, net electric field is equal to vector sum of fields of individual charges. Okay, you don't need to remember this statement, but you are supposed to remember this equation. Net electric field is the vector sum of individual fields. Okay, now coming to the next property, which is electric field exists in vacuum. As we have the equation for the electric field, E is equal to K Q by R square. I am using the magnitude representation of electric field only, electric field due to point charge. Here K is the Coulomb's constant. I can write this Coulomb's constant as 4 pi epsilon naught for free space, vacuum. Q by R square, where epsilon naught is the permittivity, of free space. You can name it as vacuum or air medium or free space medium. So if the charge is placed in any other medium, in such a case, what would be the equation? E is equal to 1 by 4 pi epsilon Q by R square. Epsilon is the permittivity of the medium in which the charge is placed. Okay, so electric field exists in vacuum as well as in dielectric medium as well, any medium as well. Okay, when there is charge, there is field. No matter what the medium is. Depending on the medium, the quantity of field changes, but however the field does exist. Now coming to the next one, electric field is independent of test charge. As we already know, electric field formula is KQ by R square. We have used the test charge representation as Q naught, but Q naught is not mentioned in any of the equations. Electric field due to point charge. It is independent of test charge. It depends on the field of the charge, charge from which the field is distributed, and the distance of the point of interest. Let's say Q is the charge and point of interest where I am going to find the electric field is this one, R. It depends, that means the electric field purely depends on the charge due to which the electric field does exist, and the distance of the point of interest from the charge R, and medium as well, medium. These are the 3 points on which the electric field depends, but not on this test charge. Okay, so electric field does not depends on the test charge, right? Now let's move on to the next statement, that is electric field decreases with distance. As I've already told you, when the electric field strength is greatest near the surface of the earth, near the surface of the earth, I mean near the charge, sorry, near the charge, near the charge. As we go away from the charge, the electric field slowly decreases, slowly decreases. I hope my point is clear to you, right? The electric field slowly decreases. When you look at this equation also, E is equal to K Q by R square. This electric field is inversely proportional to R square. As the distance increases, the electric field decreases. As the distance increases, the electric field decreases. Now let's move on to the next slide. Okay, electric field can be zero at a point in space. In the Coulomb's law equilibrium concept, we have learned that when two charges Q1 and Q2 separated by a distance r, then there is a possibility for the net force to be zero on the third charge, somewhere in between two charges, right? If the net force is zero, then the net fields also must be zero, or vice versa. If field is zero, the force also must be zero. If force is zero, then the field also must be zero. According to the equation, electric field is equal to F by Q naught. If force is zero, then field must be zero. If field is zero, then force must be zero. I hope my point is clear to you, right? Okay. So there is a possibility for the net field to be zero, So that is possible. The point where the net field is zero, electric field is zero, those points are called null points. We are going to learn about null points in the next slides. You don't need to worry about it, because I am going to give you two examples based on this null point concept. So the point where the electric field is zero, point at which electric field is zero, electric field is zero, is called null point, is called null point. Null point is the point where the electric field is zero, electric field is zero, electric field is equal to zero. Okay, so electric field can possibly be zero at any point, at some point. Okay, now let's move on to the next one. Electric field inside a conductor is zero. So we are going to learn about these conductors, insulators and semiconductors in detailed manner in the later slides. But for now, when you take a conductor, let's say I have taken a conductor. So this is a conductor, conducting sphere, let's say. The entire sphere is, solid sphere, let's say I've taken. This is a conductor. Conductor means metals. I've taken aluminum, copper, whatever the metal that we take, it's fine. Gold, okay. So let's say I've taken a metal, conducting sphere. So if I have taken a conducting sphere, let's say I've given certain amount of charge to this conductor, then entire charge redistributed on its surface, entire charge redistributes on its surface. Okay, the charge inside the conductor is zero. If the charge enclosed inside the conductor is zero, then obviously the electric field inside the conductor is zero. The net charge I am talking about, the net charge inside the conductor is zero. Individual charges will be there, will always be there, but the net charge inside the conductor is zero. Thereby the electric field inside conductor should be zero. So electric field inside the conductor is zero, since charges always redistributes on the surface of the conductor, not inside. Okay, however the net charge, total charge inside the conductor is 0. Now coming to the next point, electric field is conservative. So what do you mean by conservative? Conservative is something, the work done by this field, is independent of the path followed. It is something like gravitational field. Let's say I've already given this example. Let's say this is the object of mass m. Its gravity is acting, weight is acting vertically downwards. I've taken this object straight up. To this point. Let's say h. Now what is the work done by gravity? Work done by gravity is minus mg h. Instead of taking this object straight up, let's say I've taken this object in some other direction to the same height. Then again what will be its work done? Work done by gravity is again minus mgh. So what we have understood from this example is the work done by gravitational force is independent of the path followed. Similarly, work done by electric force also independent of the path followed. Okay, how does the electric force exist? Because of the electric field due to a point charge, right? Electric field due to a charge. So as the work done by electric force is independent of the path followed, we can treat the electric field as a conservative field. Like gravitational field, electric field are conservative. Because the work done by these fields are independent of the path followed. Hope this point is clear to you, right? Okay, let's move on to the next slide. I think the properties are properties of electric field are completed. I hope the properties of electric field, each and every property is clear to you, is very well explained to you. I hope you have understood the every explanation that I have followed, every step that I have followed. Okay, if you have any discrepancy or if you have any problem in understanding, please watch it again or comment below, so that I can respond and I can provide you more details. Okay, right. Let's look at some of the examples of electric field. I'll start with basic example and then I'll go to the complicated example as well. Now we are going to use the formula that we have learned so far. Okay, and in the later slides, in the later sessions, in the later lectures, in the next lectures, we will also obtain the expression for the electric field for different cases, like electric field due to a rod, electric field due to a ring, electric field due to a disc, and these are the concepts that we are going to learn in the next session or next lecture. Okay, so for now, whatever the formulas that we have learned so far, we are going to use them in these examples. Okay, right. Let's start with the simplest example. Let's say the electric field strength is 20 Newton per Coulomb. A charge of 5 microcoulombs is placed in the field. Find the force on the charge. Okay, we already have the formula. Force electric field E is equal to F upon Q. Okay, as the direction is not asked, direction is not even mentioned for the electric field, I am using the magnitudes only. Okay, now if I rearrange this formula for the force, as I need to find the force, F is equal to EQ. E is how much? is 20 Newton per coulomb into Q is how much? 5 microcoulombs. 5 microcoulombs. And the term micro means 10 to the power minus 6 coulombs by 1 microcoulombs. Okay. So what am I getting? 2 5s are 10, 10, 100, 100 means 10 to the power minus 4 newtons. Force on the charged particle is 10 to the power minus 4 newtons. Okay. Since the charge is positive, the force on the charge is along the direction of the field, along the direction of the field, along the direction of the direction of field. Let me elaborate this point again. Okay. Now let's say electric field. I've taken a charge Q. And the field is all around. The field is existed around this charge. Now I've taken another charge of charge Q0, another point charge of charge Q0. I placed it somewhere here. Okay. Now this force between the two is repulsive. Okay. Now this Q0 experiences the force in the direction of field. As I've already told you, this is a positive charge, so the field is radially away, and we are not interested in any of the field. We interested only the direction of field towards the test charge. Okay, point of interest, as I can say, point of interest. At this point the field is away. Because this is a positive charge. So field is away. So field is away means this Q0 will try to move in this direction only, right? In the direction of field. Instead of taking the positive charge, let's say I've taken negative charge. So, and I've taken Q0 in the field of the negative Q charge, okay, minus Q charge. Then what happens? Separation between them is this one, and the field due to minus Q is towards the charge. This is the point that I have already explained in the properties of electric field. As the field is in this direction, this minus Q charge attracts this Q0 charge, right? So the direction of Q0, direction of force, I am representing the electric field direction, okay, electric field direction and electric force direction as well, okay. Electric field direction is this one, electric force also in the same direction, as long as you are using the positive test charge, okay. Now field due to a positive point charge is radially away, field due to negative point charge is radially inward towards the charge. Where am I measuring this field? Exactly at the point of interest. I don't care about the rest of the field lines. I care only about the field line exactly at the point of interest. I hope I made my point clear here, right? Okay, right. So this is one such example. Okay, I'm going to erase this one. Let's move on to the next example. Okay, next example. Let's take an equilateral triangle. So this is, and here we have a charge Q, and here also we have charge Q, and we have the third vertex as well. This is a point where we need to find the electron, where we need to find the electric field. I'm naming this point as P. Find the electric field at point P. I'm representing the vector here because I want to find the magnitude as well as the direction. as well as the direction. So this is an equilateral triangle. Equilateral triangle. Equilateral triangle. I am considering each side as R. Each side as R. Okay, right? Now is the question clear to you? Right? Okay, let's solve it. Now, okay, now I am going to draw the diagram again. Okay, so charge Q. Here we have third point P. Now, so the electric field due to this positive charge, what is our point of interest? Point of interest is P. I am going to measure the electric field due to this point charge at here, due to this point charge again at here. Okay, so I am going to consider only one charge at a time. Okay, now field due to this charge, as this is positive charge, it is radially away. I am considering it as E1 vector, let it be E1, and this is also Q, which is positive again, which is radially away. This is E2. Now I am going to find the equations for E1 and E2. Then I add these two electric field vectors by using superposition principle. Right? Okay. Now let's write electric field due to charge 1. E1 vector. I am going to find the magnitudes first and then I add them vectorially. So electric field E1 is equal to KQ by R square. KQ by R square, because this is R, this is also R. We have used the formula for the electric field due to a point charge. So point of interest distance is R from the point charge. Here also point of interest distance is R from the point charge. And E2 is again KQ by R square. And we come to a conclusion, E1 is equal to E2. Magnitudes only. Okay. Magnitudes are same. Now coming to the directions are different, as we can already identify here. Both of them are moving in different directions. Now what I am going to do is, I am going to resolve these vectors into x and y axis. So this is a you can even directly use the parallelogram law of vectors, but I'm doing the resolving of vectors here, and then I follow the simplest method as well. So E1, what will be this angle? 60 degrees. And what will be this angle? 60 degrees. This angle also will be 60 degrees, because it is an equilateral triangle. If this angle is 60, then this angle also will be 60 degrees. If this angle is 60, this angle also will be 60 degrees. Now let's resolve these vectors. E1 vector is resolved towards this axis, E1 cos 60, and if this vector is resolved here, E1 sin 60. Similarly resolve this vector, E2 cos 60 and E2 sin 60. As we already know, the magnitudes of E1 and E2 are same. So E1 is equal to E2. So E1 cos 60 will get cancels. What am I left with? E1 sin 60, E2 sin 60. As we already know, E1 is equal to E2. So net field field net is equal to sum of these two, right? Sum of these two. These two get cancelled. We left with only two components here which are acting vertically upwards. So E1 sin 60 plus E2 sin 60 again. And I know E1 is equal to E2. So E2 can be written as E1 itself. Right? Now E net is equal to E1 sin 60. E1 is how much? KQ by R square. KQ by r square sin 60. Sin 60 is sin 30 1 by 2 root 3 by 2. Sin 60 is root 3 by 2 plus E1 is again kq by r square root 3 by 2 again. What are we left with? 2 times kq by r square root 3 by 2. 2 will get cancelled. What do we left with? Root 3 k q by r square. So this is the net electric field at the point of interest, at the third vertex. At the third vertex. If you want to say the direction, along y-axis, along y-axis, positive y-axis, which is upwards, If you place a charge, let's take the same diagram again. So this is one charge and it is the point of interest q, and here let's say I have placed capital Q. Now if I asked you to find the force on this capital Q, then we need to find the field at this location. The field is electric field at point P. Electric field at point P is how much? Root 3 k q by r square, because each side is r itself. Now I have asked you to find the electric force on Q. To find the electric force on Q, force is equal to E into Q. We have already learned this formula, right? So if I know the charge and the electric field, I can find the force by using this relation. Instead of small q, here you are given with capital Q, right? So instead of small q, I am writing capital Q. So F is equal to E is how much? Root 3 k small q by r square into capital Q. This is how you can even find the force on the charged particle. After finding the field at that point. I hope this example is clear to you, right? Okay. So let's move on to the next example. Okay, right. Let's look at another example. Let's define a question here. Let's take a square. Okay, charge is arranged on a square. So this is a square where I have placed the charges here, and here. Okay, let's say I have taken the charge here also. Let's say now I want to find the net electric field at the center of the square, Let's say here the charge is q, here the charge is q, here the charge is minus q, here the charge is minus q again. Okay, now the field due to positive charges towards this one. Let us suppose this is 1, 2, 3, 4. Okay, electric field due to point charge at location 1 is E1 acting away. Electric field due to 3 is E3 acting away, because these two are positive charges. Electric field due to charge at location 2 is toward, because charge is negative, E2. Okay, now we have another charge E4 towards again E4. When you look at the quantity of charge and the distance and the medium in which they are placed are all same. Okay, when you look at E1 and E3, is equal to KQ. Both of them are having same charge. So KQ by distance also same. Let's say I have taken R distance, as each side. Now this half of the diagonal is r by root 2, r by root 2, r by root 2 whole square. Both of them are same, right? That means these two fields are acting in opposite direction with equal magnitudes. That means E1 vector is equal to E3 vector but in opposite direction. That means they both cancel out each other. So these E3 E1 will get cancelled. Similarly, if we look at the rest of the two, E2 and E4 is equal to K Q by R by root 2. I am writing the magnitudes only square. These magnitude also same, right? So KQ by R by 2, distance also same, they are placed in the same medium. So the field will be same, KQ by R by root 2 whole square, right? So these two also, E2 is equal to E4 but in opposite direction. That means E2 and E4 also gets cancelled. What will be the net field at point O? Electric field at O is how much? The question is. Electric field at O is equal to 0 because all the fields are cancelling out each other, resulting to 0 electric field. This is one point where the electric field is 0. We call this point as null point. This point as null point because the field is 0. Okay. So I am going to take the same example again with the different charges. Okay, let's arrange this one. It is the simplest example. Let's make it little bit complicated. Okay, I am going to take the square again. Square where I have placed Q and Q. All the charges are same, let us say. Now I have asked you to find the electric field at this location, at point P. Find the electric field at point P. I am going to write the vector representation of electric field at point P because I want to find the magnitude as well as the direction. Okay, right. Okay, now first this is location 1, location 2, location 2, location 3. Okay, now first find the electric field due to point charge at location 1, E1. Let's say this is R and R. Okay, all the sides are same, which is equal to R. Now KQ by R square, along x-axis. I am representing the directions here, which is E1 vector. Okay, now E2 is how much? E2 is equal to KQ by R square again because the distance is R, charge is Q, but the direction is away, radially away, E2. Now coming to the third charge, that is Q. Okay, E3, KQ, charge is same, medium is same, but the distance is this one. This one. How much is this distance? R root 2 R because the diagonal. Okay, root 2 diagonal, root 2 R. Okay, root 2 R whole square, So 1 by 2 K q by r square, 1 by 2 kq by r square. So this is the electric field due to the charge, point charge at location 3. Now I want to add these vectors, add these electric fields in vector form, or I can find the resultant of these two and then add them. Okay, now first I am going to use the vector representation first, and then I use the regular method. Okay, so E1, let's say let's use the regular method. It would be easier to find it. In the earlier case we have seen adding the electric fields in vector representation, right? But this case let's use the regular method of using parallelogram law of vectors. Okay, so E1 and E2 are acting perpendicular direction. The resultant of E1 and E2, E12, resultant of these two. So this E3 will be in this direction, E3. Okay, right. So E12 is equal to E1 vector plus E2 vector. E1 vector plus E2 vector. I am using the parallelogram law of vectors to find their magnitude. So E12 magnitude, as these magnitudes, E12, 12. Okay, as these two vectors are acting in perpendicular direction, the resultant will be E1 square plus E2 square. E1 square plus E2 square, as you already know. If this is the point, it is x, it is y, then r magnitude is equal to x square plus y square, right? So this is how we find the magnitude. Same concept I have used here. This E1 is acting along x axis, E2 is acting along minus y axis. So I am using the magnitude squares, adding them to get the magnitude. Right. Now I'm replacing the expressions here. Kq by r square, Kq by r square whole square, again Kq by r square whole square under root. So what am I getting? Kq by r square common can be taken, Kq by r square whole square can be taken common. 1 plus 1 is root 2. So root 2 Kq by r square, magnitude of resultant of these two, resultant electric field of these two vectors, and the direction of these two, direction of resultant is along this direction only, along this direction. How do we find the direction of the resultant? Tan theta, by using the slope equation, which is y by x, here Ey by Ex. Okay, now tan theta is equal to Ey is how much? Kq by r square. I am using the magnitude, Kq by r square. Ex is how much? Kq by r square again. If it is cancelled, what we left with? 1. It is possible only when theta is equal to 45 degrees. 45 degrees. So this will be 45 degrees and this will also be 45 degrees. So the electric field E12 will be in the same direction as that of the E3. Now we already know the vectors which are in the same direction can be added directly. So to find the net electric field at point P, which is E123, E123, right? Electric field at point P is nothing but E123. We already know E12 and we have E3 again. So E12 plus E3, we can add them directly because these two vectors are in the same direction. We can add them directly. E12 is how much? Root 2 times Kq by r square, root 2 times Kq by r square, plus E3 is how much? Which we already know, 1 by 2 Kq by r square, 1 by 2 Kq by r square. I can take Kq by r square as common because it is the term that is there in the two terms. Kq by r square, root 2 plus 1 by 2, root 2 plus 1 by 2, root 2 plus 1 by 2. So this will be our answer, electric field. electric field. Okay, we have another method to find it also by using the vector representation. Okay, that also I am going to do, right? I am going to do it here only. So I know E1 vector is equal to kq by r square I cap, because it is along the x-axis. It is along the x-axis. I have another vector E2 vector is equal to again kq by r square minus j cap, because it is along the negative y-axis. Negative y-axis. I have the E3 vector which is kq by 2r square, kq by 2r square in this direction, right? And this is 45 degrees. I can write this as cos 45 I cap minus plus sin 45 j cap minus j cap whole into, right? So when you look at this F3 can be resolved into two components. F3, one component is along I cap, that means x axis, other component is along minus j cap, that means along minus y axis. I have taken kq by 2r square common because it is there in two terms. So I have taken that common, cos 45 cap x component and minus sin 45 j cap which is y component. Okay, so E3 I am writing it again. So cos 45 is 1 by root 2, 1 by root 2, 1 by root 2, 1 by root 2 kq by 2 root 2 2 root 2 r square I cap minus j cap, I cap minus j cap, I cap minus j cap. So if you add these vectors, if you add these vectors, this one E1, E2 and E3, you will get the resultant vector. We have kq by r square as common, kq by r square as common. Okay, if you take that common, EP is equal to kq by r square. I am using the direct steps here, in this explanation, because it is the second method of solving this question. Okay, so kq by r square, we have I cap and here also we have I cap. So 1 plus 1 by 2 root 2 I cap, we have minus j cap and here also minus j cap, minus 1 plus 1 by 2 root 2 j cap, minus. Here we have minus because y components have negative sign. If you find the magnitude, you will get this one. If you want to find the direction, you will get 45 only, because x component and y components are same. X by y will give 1, which means it will be at 45 degrees above or below x axis, below x axis. I hope this explanation is clear to you, right? So it is a little bit complicated question. If you want to make it complicated, we are going to take another example with the three-dimensional arrangement of charges. We use vector representation of electric field to find the required quantity, net electric field. That required quantity is nothing but net electric field. Okay, let's move on to the next example. Right. Okay, I'm going to define the example here. I'm going to take a three-dimensional arrangement of charges. Okay, square pyramid, I'm taking it as example. Okay, and we have charges here, here, here and here. Okay, right. So here I have q charge, q charge, q and q, q and q, and there is a point where we need to find the electric field. Electric field at point P. Electric field at point P is how much? That's the question. So this is a square pyramid. So I have this. Okay, square pyramid. And I have the center here. Okay, and each side is root 2a, root 2a, root 2a. Each side is root 2a. each side is root 2a. Okay. Now if this is root 2a, this is root 2a, this is root 2a, I am considering this height as a. Height as a. Height as a. In such a case, if I consider the center as the origin, then I need to find the electric field at point P. I have to use the vector representation of electric field due to a point charge. Okay, right. Now I am naming the charges. This is location 1, location 2, location 3, location 4. Write it. So to use the vector representation of electric field due to a point charge, I have to define the x and y axis first. Okay, I am going to define the x and y axis, something like this one, x axis. Okay, and y axis is this is y axis, x axis and y axis. Okay, now I am going to define the locations of the each charge. Okay, now q at 1, q at 1, q at 1, this is on the negative x axis, so y component is 0, z component is also 0, only it will have x component without to negative. So minus a 0 0, minus a 0 0, in vector notation minus a I cap, minus a I cap. So q1, I am directly writing the vectors of each charge. q2, it is on the y axis, positive y, positive, x component is 0, a 0, in vector notation it is aj, and third charge it is on the positive x axis, a 0 0, how much, ai cap. And about fourth charge q, it is on the negative y axis, so 0 minus a 0, which is minus aj, okay, now I have defined the vectors of the positions of each charge, Now I am going to define the position of point P with respect to each charge, let's do that. So position of point P with respect to 1, position of point P with respect to 1, position of P minus position of 1, position of P minus position of 1. Position of P is how much? It is on the z axis, so this is the z axis, 0 comma 0 comma a, 0 comma 0 comma a, that is in vector notation a z cap, a k cap, k is the unit vector here, okay, along z axis, a k cap minus r1 is how much? Minus ai cap, which is a k cap plus a I cap, position of P with respect to 1. Similarly, position of P with respect to 2 is, position of P is a k cap minus position of 2 is a j cap, position of P with respect to 3, a k cap minus third one is a I cap. Similarly, position of P with respect to 4, which is a k cap minus a j cap, which is a k cap plus a j cap. So these are the positions of point P with respect to 1, 2, 3, 4 locations. Now let's write the electric field equations for each point charge at point P. Electric field at point P due to charge 1, which is k q by distance is how much? kq by magnitude r p1 magnitude q into r p1 vector representation of electric field. Magnitude of r p1 is root 2a by magnitude of p1 root 2a cube, we have cube here, and rp1 vector is a can be taken common, that I am writing here, k cap plus i cap. Okay, now let's move on to the next one, ep2. We will get the same equations, but the vector, the unit vectors will change. So k q a by root 2a whole cube rp2 is a can be taken common, that I have already taken common, k minus j. Okay, similarly ep3 is equal to kqa by root 2a whole cube into k minus I, k unit vector minus I unit vector. Similarly ep4 is equal to kqa by root 2a whole cube into unit vector notation is k plus j. Okay, so to find the net electric field at point P, we use superposition principle. As we have already learned about superposition principle, according to superposition principle, the net electric field or the resultant electric field is the vector sum of individual fields. So I am doing the same here. Electric field at point P is equal to ep1 plus ep2 plus ep3 plus ep4. ep1 is how much? kqa by root 3a whole cube, kqa by root 3a whole cube, kqa by root 3a whole cube. All the terms are common in all the electric field equations. I am taking it as common, kqa by root 2a whole cube. Root 2a whole cube can be written as 2 root 2a cube. So I can write this as 2 root 2a cube. Okay, 2 root 2a cube, and we have 1a on the numerator and a cube in the denominator. If I cancel out these two terms, we will have a square in the denominator. So I am directly writing the terms a square in the denominator, and here I have k plus I cap plus k minus j cap plus k minus I cap, k minus I cap, and we have last term which is k plus j cap, When you look at this equation, all I cap minus I cap cancelled, j cap minus j cap plus j cap cancelled, k 4 k's will remain. So 4 times k q by 2 root 2 a square, 2 2s are root 2s are. So finally electric field at point P is root 2 kq by a square. So this is the answer. I still have one term left, which is unit vector notation. And here also we have unit vector notation. I have used a different color for this k cap because here this k and this k are not same. So this small k is Coulomb's constant, and this k is the unit vector along z axis,
axis.
Along z axis. So these two are different quantities. K cap is the unit vector along z axis which represents the direction of electric field, net electric field. K, small k is the Coulomb's constant, which is the which has the value of 9 into 10 to the 9. So this is the net electric field at point P, which we have determined by using the help of vector representation of electric field due to a point charge. I hope this entire analysis is clear to you. The same example we have seen it in Coulomb's law also, vector representation of Coulomb's law also. There we have discussed 2 to 3 examples. Okay, if you want to verify those examples also, please check out my channel. Okay, let's move on to the next example here. Null points. We have already learned this concept in Coulomb's law equilibrium lecture. Okay, so in Coulomb's law equilibrium lecture we have understood that the net force acting on the third charge, which is placed between the two charges or beyond the two charges, can possibly be zero. Okay, so if the net force acting on the third charged particle is 0, then there is a possibility for the net field also to be 0. Okay, we are going to learn null points concept again here. Okay, without considering the third charge, just considering the point. Okay, right. The term null point means the point where the electric field 0, not simply the electric field, the net electric field is 0. Okay, so I am going to take an example to make you understand it even better. So example, I'm going to take 2 examples. Okay, in one example I'll take 2 similar kind of charges, that means positive or negative. In the other example I'll consider one positive charge and the other one is negative charge. Okay, right. Let's look at the first example here. Now I'm taking the charge Q1 and Q2. These two are separated by a distance r. Center to center distance is r. Now, as we have already learned, I am going to divide the regions around these two charges into 3 parts. One is this one, region 1, region 2 and region 3. Okay. Now let us consider the point of interest where we need to find the electric field. Okay. Let us suppose I have considered the point somewhere here in this region 1. Now what happens? The field due to positive charge is always radially away. That means field due to Q1 is radially away in all the directions. But we are not interested in the entire field which is produced by charge Q1. We are interested in the field that is along the line joining the point and the point charge. So I am going to consider the field along this direction only. As I have considered the positive charge, the field is always radially away. So at the point of interest, the field is along this one, left side. And field due to Q2 will also be in the same direction because this is also positive charge. The point of interest is again same. Okay. Now the field is again this direction. When two fields are acting in the same direction, then there is no possibility for the net field to be 0. So there is no possibility for the net field to be 0. Right. So net field not at all be 0. Now let's take the point in region 2. Again the same story will repeat, but in the earlier case we have seen the electric field direction is leftward, but in this case the electric field direction will be rightward because this is a positive charge, rightward, radially away, and this is again a positive charge which is also radially away, as the point of interest is same for both the charged particles. Now instead of taking, let me erase this one. Okay, instead of taking the charge on these two sides, let's take the charge in between let's take the point in between the two charges. I am considering the point somewhere here. I'm considering the point somewhere here. Okay, I have taken the point. Now I have to measure the electric field. I have to find the electric field at this point, and I have to make sure the net field at this point should be 0. That means the fields due to both the charges must be of equal magnitude but of opposite direction. They must be acting in opposite direction. Let us suppose the field due to charge q1 is E1, which is to the right. Okay. Now the field due to q2 is E2, which is to the left. As two fields are acting in opposite direction, if their magnitudes are same, then the net field can possibly be 0. So for the at the location of null point, the net electric field to be 0. E net to be 0. E net to be 0 in the sense E net is nothing but E1 minus E2, because the two fields are acting in opposite direction, which must be equal to 0. So according to this equation, if I rearrange this equation, E1 is equal to E2. That means the magnitudes of electric field must be same. So E1 is nothing but K Q1. Let us suppose this distance is R1. Now this distance, let it be R2. Now Q1 by R1 square is equal to K Q2 by R2 square. Right? Hope this point is clear. If I cancel this K on both sides, what am I left with? Q by R1 square, Q1 by R1 square, Q2 by R2 square. As we already know, for the net field to be 0, the ratio of Q1 by R1 square, Q2 by R2 square must be same. These two ratios must be same. That is possible only when charge Q1, let's say charge Q1 is less than Q2. Their magnitudes are related as per this relation. So Q1 is less, Q2 is more than Q1. In such a case, if I consider the point very far from this Q1, then the ratio will be very less. And if I consider the point somewhere here, let's say somewhere here, okay, if I consider the point somewhere here, then what happens? Q2 and distance is very less. If the distance is less, the ratio will be more, and Q2 is already more than Q1. That means this ratio will be bigger than this one. There is no possibility for these two ratios to be equal, right? Hope my point is clear. Now what I am going to do is, I am going to take this off. Okay. Now I am going to consider the point near the smaller charge, so that as the distance is smaller, that means the ratio of 1 by R square is bigger into Q1 is smaller, right? So big into small, and here big into 1 by R2 is large, longer distance. So 1 by longer distance square means small value, small into large is again. There is a possibility for the two ratios to be equal at particular distance, okay, which should be close to the smaller charge. And if you want to learn about this, equaling the ratio, please watch my equilibrium concept, electric field equilibrium lecture. Coulomb's law equilibrium lecture. You will be able to understand it very clearly. Okay. Now, as we have considered the point in between the two charges, that too close to the smaller charge, I am going to write the equations. Okay. Now, instead of taking this R1 and R2, I am going to erase this one. Okay. Right. Okay. Now, instead of I am going to take one more. Okay. Instead of taking R1 and R2, I am going to consider these distances as x, and this will be R minus x. Hope you have understood this. If this total distance is R, as I have already mentioned here. Total distance is R. Now, if point is considered from the smaller charge is at a distance x, then the rest of the distance will be R minus x, right? Now what I am going to do is, I am going to write the electric field equation E1 K Q1 by x square K Q2 by R minus x whole square. If you solve this equation, kk will obviously get cancelled. If you solve this equation, you will get, what you will get? So r minus x by x whole square, if I'm not wrong, if I rearrange this equation, r minus x by x whole square is equal to q2 by q1. Okay, hope you know how to rearrange this equation, right? R by x minus x by x is 1 whole square in q2 upon q1. I'm taking this square of, I'm putting the root here because I'm applying the square root on both sides. Square and square root will get cancelled, and here we will get square root. So if I rearrange this equation, r by x is equal to q2 by q1 under root plus 1. If this minus 1 is taken to that side, you will get plus 1. I want the null point, that means where the electric field is 0. I want the null point is to be measured from a reference point. That reference point can either be q1 or q2. In this case, I have taken q1 as the reference point because I have considered x distance from q1 itself. So x is equal to r by root over q2 by q1 plus 1, and this root is not for this plus 1, it's only for the ratio of q2 by q1, and q2 and q1 are magnitudes without sign. Hope you have understood this one, right? Now let's move on to the next example. In the next example, we are going to consider one charge as positive, the other charge as negative. In such case, you won't get the null point in between the two charges, rather you will get the null point beyond the two charges, but the condition is, again, that null point is to be obtained, is to be considered near the smaller charge, right? Let's move on to the next example. Okay, let's take the example again, let's define the example again. I'm taking q1 here and q2 here. Okay, separation between the two is r again. Okay, now what I'm going to do is, I'm going to consider negative sign for one of the charges. Let's take negative sign for this one. q1 is negative, q2 is positive, but however, I know the magnitude of q1 is less than magnitude of q2. Magnitude of q1 is less than magnitude of q2. In this case, the null point is near to q1 itself, but beyond the two charges. Either you will obtain the null point either this side or that side, but however I have considered q1 as smaller charge, the null point will be obtained near to smaller charge itself. You will get the null point somewhere here. Let me explain how. Okay, let's say this is the line. Okay, now this is region 1, region 2, region 3. Let's understand it. Okay, now let's consider the point in region 3. If I have considered in point in region 3, the field due to negative charges to this side E1, the field due to positive charges again to this side, positive charge radially away, negative charge radially towards. So field again to this side. There is no possibility for the net field to be in opposite direction, and there is no possibility for the net field to be 0. Okay, individual fields are not in opposite direction, so there is no possibility for the net field to be 0. Okay, now what I am going to do is, I am going to consider the point somewhere here. Null point is possible, but however, if you look at the ratios of q1 by r1 square, q2 by r2 square, you won't match the ratios if you consider the point here, because this charge is greater. If you consider the point near to this greater charge, again the ratio would become increases rather than matching with the other ratio. Okay, instead I have considered the point here. I am going to erase all these things. Okay, I have considered the point here. So this could be our null point. Now let us find the electric field due to individual charges, and I'm going to take these things off. Okay. So electric field due to minus charge is to the electric field due to minus charge is towards the negative charge. I mean negative charge is towards the negative charge, which is E1, and electric field due to positive charge is away from the positive charge. So these two fields are in opposite direction, as you can see. Okay, these two fields are in opposite direction. If these two fields are in opposite direction, then E1 is equal to E2. Let's say I have considered a point at a distance x from the reference charge, that is minus q1, that I have considered in this case. So I am going to consider the magnitudes only. E1 is nothing but k q1 by distance is x square, and E2 is k q2 by how much is this one? This entire length is r plus x, as you can see. This entire length is, this is r, from charge q2 to null point is r plus x. This is r and this is x, r plus x. So I am writing here r plus x whole square, cancelling this case and rearranging this equation, r plus x by x whole square. In the earlier case we have got r minus x by x, but in this case you will get r plus x by x whole square. We will get q2 by q1. As I have already mentioned, I have taken the magnitudes only. I haven't considered the negative sign because I am using the magnitudes of charges in the formula. So r by x plus 1 whole square can be cancelled, and I can put root here. So root over q2 by q1. If I rearrange this equation, r by x is equal to root over q2 by q1 minus 1. I have taken this plus 1 to that side. I have got it here, that is minus 1. I need x value because I am finding the null points from the reference charge. That reference charge is q1 itself. So x is equal to r upon root over q2 by q1 minus 1. Again, this q2 and q1 are magnitudes only. We don't consider the sign. So these are the best examples for the null point. Okay, hope you have understood the entire lecture and these examples as well. Okay, if you find any difficulty in understanding, please watch it again, and if you still find any difficulty in understanding, please comment below. Okay, so that I can help you, I can give you some more details to make you understand it better. Okay. So yes, if you really like this video, if you find the video is really helpful, please like, share, subscribe, and don't forget to hit the bell icon in order to get the notifications as soon as I upload the videos. That's it in this video. Thank you for watching. See you again in the next video. Thank you.